Think you've seen everything about World War II tanks? Think again. There was one machine that was a nightmare for minefields, and yet could save the crew's lives. But at the same time, its own design often turned them into targets. The tank known as the Sherman Crab had deadly quirks, from chains that could snap at any moment to dust and explosions that turned the crew into invisible heroes on the battlefield. From the moment tanks appeared in combat, they were seen as nearly invincible. Armored vehicles offered crews relative protection from bullets and bayonets, creating the illusion that fighting inside a tank was safer than being out in the open. But battlefield experience quickly proved that even the heaviest machines were vulnerable to deadly landmines. With each battle, opponents found new ways to destroy armor and disable tanks. For commanders, this posed a serious challenge. Tanks were expensive, and losses in minefields were rising fast. It might have seemed logical to abandon tanks, but in practice, armor and mobility remained crucial, and tank design continued to evolve. Against this backdrop, the idea of a special engineering solution emerged, something that could protect tanks from mines. It first took shape in Britain when troops were sent to North Africa, where fierce battles raged. Tank losses to mines were staggering. By 1941, nearly a quarter of all destroyed vehicles had fallen victim to minefields. Meanwhile, German industry was producing hundreds of thousands of mines annually, keeping the threat constant. Ordinary tanks on these fronts became vulnerable targets, and this spurred British engineers to find unconventional solutions that could clear mines while preserving tank mobility. The solution was simple, yet brilliant. Attach a device to the tank that could safely destroy mines before they reached the armor. The design featured a rotating drum with chains, each ending in a roughly 2-kilogram weight. As the tank moved forward, the drum spun, swinging the chains against the ground to detonate or destroy mines at a safe distance. The idea was so effective in theory that military command immediately approved it. The first tank modification to use this system was called the Sherman Crab in 1943. It wasn't a new tank, but an upgraded version of the American Sherman series. British engineers adapted the original hull to mount the flail, keeping the tank's basic specs largely unchanged. The first production model entered service in 1944 after a series of refinements and tests. Officially designated Sherman Crab II, the name never really caught on. Soldiers quickly nicknamed their machines simply Crabs, inspired by the rotating chains at the front. Although the Sherman Crab didn't get to prove itself in North Africa as planned, it played a key role in Europe after the Allied landings. The tanks cleared paths through minefields, speeding troop movement and reducing losses among infantry and vehicles. 3 tanks led the way, opening a lane about 7 meters wide, while 2 more flanked them, ready to replace any damaged vehicles. This approach ensured continuous movement for the columns and minimized risks for the rest of the units. Operating the Sherman Crab was not without its challenges. The constant spinning of the chains kicked up clouds of dust, completely blocking the crew's view. Crews often had to move blindly, sometimes colliding even with friendly tanks. Exploding mines also damaged the flail chains, which had to be replaced on the battlefield. This slowed progress and exposed the tanks to enemy anti-tank fire. Despite these drawbacks, the benefits far outweighed the problems. Crabs accelerated troop movement, reduced losses, and allowed safe passage through minefields once considered impassable. By the time Sherman Crabs reached European battlefields, their full potential became clear. Leading columns, they methodically cleared minefields that were previously deadly. But maneuvering in combat wasn't simple. Dust clouds from the flails blocked all side and rear vision, leaving crews only glimpsing the outlines of the tanks ahead. This led to constant collisions, sometimes even with friendly vehicles, putting extra pressure on commanders. The tactics for using the Crabs were carefully honed. 3 tanks moved ahead to clear the path, while others followed on the sides, ready to replace any flails that broke down. The cleared lane was about 7 meters wide enough for infantry and armored vehicles to pass. Crews had to work in perfect sync, as even a small mistake could trigger a mine too close to the tank, damaging the flail or hull. The constant vibrations and impacts from the chains wore down parts quickly, so mechanics had to repair worn components right on the battlefield. Despite the difficulties, Sherman Crabs were remarkably effective. They reduced losses among personnel and equipment, which was especially valuable against stubborn German defenses. On narrow roads and in urban areas where mines could be hidden under pavement or debris, the tanks created literal safety corridors, ensuring continuous movement of Allied columns. Over time, crews learned to anticipate the flail's motion and minimize collisions, developing their own internal rules for movement and signaling. The psychological impact was just as important. Soldiers who saw the Crabs effortlessly clear mines under the tracks felt more confident and less fearful of sudden explosions. This boosted morale was particularly noticeable among infantry moving behind the tanks. The enemy, in turn, tried various methods to neutralize the Crabs. Germans set up extra anti-tank obstacles, larger mines, and even ambushes with anti-tank rifles. Yet, in most cases, even heavily prepared minefields could not stop the Crabs. Operating a Sherman Crab required skill and discipline. Crews had to monitor chain integrity, adjust speed and direction, and account for terrain and mine density. Any deviation from the planned course could have serious consequences. Nevertheless, tank crews quickly mastered their machines. British mechanics carried spare chains and weights on board so they could be replaced quickly if damaged. Beyond mines, the tanks faced additional challenges. Explosions remained powerful, often straining the flail, forcing multiple tanks to work the same area. Dust and mud clogged mechanisms, and the constant rotation of the drum increased stress on the tracks and engine. But despite these obstacles, the Sherman Crab proved its worth. On the battlefield, it saved time and effort that would otherwise have been spent clearing mines by hand or navigating around hazardous areas. By the time of the Allied landings in Normandy, the Crabs were an essential part of armored engineering support. Their presence not only protected against mines, but also boosted morale. Soldiers knew they could cross deadly terrain with minimal risk. Experience showed that even small adjustments, chain length, weight of the flail weights, could significantly impact effectiveness, and engineers constantly refined the design on the front lines. When the Allies landed in Normandy, the Crabs took on the most dangerous engineering task, breaching mined beaches and pushing inland. In the early hours, the goal was less about destroying enemy positions and more about opening paths for tanks and infantry. Without these lanes, columns would have stalled under fire. The machines flailed the ground, smoothing obstacles and allowing supply transports and reinforcements to reach the front lines. Where a soldier with a shovel moved slowly under fire, the Crab acted quickly and relatively safely. Operational examples highlight the importance of reliability and coordination. On one sector, 3 flail Crabs were clearing a dense minefield when the enemy launched a counterattack from side bushes. Dust obscured targets, visual contact was lost, and any tank guns and rifles fired from ambushes. Crews followed established procedures. Reserve tanks covered flanks, artillery suppressed enemy positions, and mechanics risked exposure to replace damaged chains. The mission succeeded, though time and resources were costly. One tank was disabled, and repairs took several hours. The Germans, observing the flail tanks, developed countermeasures. Ordinary mines were replaced with larger charges. Double or triple sets were installed, and cable detonators or incendiary devices so the field remained dangerous even after the first flail pass. Sometimes combined traps were deployed. A mine with a delayed fuse exploded when the next chain hit, directing the blast toward the tank hull. In some cases, a broken chain damaged the flail, but the armor remained intact due to the detonation distance, considered a tactical success. Interestingly, in some operations, the Crabs were used not just as mine-clearing tools, but as psychological weapons. Moving in close contact with infantry, they deliberately led the way, provoking the enemy into firing and revealing machine gun and artillery positions. Soldiers hiding in cover hastily counterattacked, only to face tactics already anticipated by Allied infantry and armor. In effect, the flail became both an engineering instrument and a tactical tool. Maintenance experience was equally important. Tanks carried spare chains and tools, but replacements often had to be made in mud under fire, a task for the most resilient crews. Veteran tankers frequently modified mounts and reinforced components based on observations, adjusting chain length, changing flail weight, adding extra shock absorbers to reduce transmission wear. These field improvements later informed official instructions and design updates. Another key lesson from the war was the importance of combined operations. Sherman Crabs were most effective when coordinated with engineering units, sappers, and air support. Artillery suppressed likely mine emplacement points, sappers cleared especially dangerous areas, and aircraft provided reconnaissance and fire adjustment. Without such coordination, the flail alone was only half as effective. The human factor was equally critical. For drivers, mechanics, and commanders, the Crab was a school of resilience. Operating in constant mud, vibration, and danger required not only technical skill, but discipline. Many who served with the flails throughout the campaign recalled the satisfaction of a completed mission: cleared lanes, alive comrades, and flexible tactics, all making their work tangible and meaningful. By mid-campaign, the Sherman Crab had firmly proven its value. It was not a luxury experiment, but a practical tool capable of changing the course of operations in mined areas. With proper preparation and coordination, it saved time and lives. And when the enemy invented new traps, crews quickly learned how to counter them. When Normandy was breached and Allied forces advanced deeper into Europe, the Sherman Crab became a symbol of the engineering approach to warfare. The tanks showed that even a complex, expensive vehicle could be transformed into a versatile instrument, solving strategic problems not just with firepower, but with control over terrain. The flailed lanes allowed large-scale offensives, reduced casualties, and accelerated the pace of combat. Where regular tanks and infantry hesitated before minefields, the Crab kept the advance moving. The engineering lessons of the war were invaluable. Thoughtful mechanization, field modifications, and careful maintenance showed that a simple idea, a rotating chain flail, needed precise integration with tactics and crews. Experimental improvements made on the battlefield became a vital source of knowledge for future generations of engineering vehicles, from World War II mine flails to modern armored demining units. Crews shared insights on optimizing chains, shock absorbers, flail rotation speed, and coordination with artillery and infantry, enhancing the overall operation's effectiveness. Despite obvious drawbacks, dust, chain replacements, and mechanical damage from explosions, the Crabs demonstrated that armored engineering tanks could be decisive. Moreover, enemy observation of their work prompted the creation of new mine types, chain trigger devices, and traps, driving further innovation in engineering thought. The competition between technology and tactics became a hallmark of World War II, where every new development required immediate adaptation. After the war, the legacy of the Sherman Crab influenced armored engineering vehicles worldwide. The concept of safely neutralizing mines and explosives, protecting columns, and creating passageways for infantry and armor became standard practice. Normandy proved that battlefield-driven innovations could radically alter offensive operations and reduce losses. In the end, the Sherman Crab entered history not as a mass combatant, but as an engineering tool demonstrating that armor and weapons were only part of victory. Controlling space, ensuring troop movement, and protecting crews' lives, that was the true value of such machines. Flail tanks became the first step toward modern engineering units, capable of solving complex tasks under extreme danger while maintaining speed and operational efficiency. Today, Looking at photos and reports of the crabs, it's easy to see the brilliance in combining a simple idea with effective implementation. What might have seemed like an odd experiment turned out to be an indispensable part of Allied tactics. And while their direct use ended with the war, the legacy lives on in engineering solutions designed to safely and rapidly overcome minefields around the world. The Sherman Crab's legacy extends beyond World War II, influencing modern combat engineering and demining operations worldwide. Its concept, a rotating flail, to safely neutralize mines, set a standard for protecting advancing forces and ensuring the mobility of armored and infantry units. The lessons learned in Normandy demonstrated that simple, well-integrated engineering solutions could drastically reduce casualties while accelerating operational tempo. This tank was not just a weapon, it was a tactical tool. By controlling terrain, opening safe corridors, and supporting infantry movement, it turned the battlefield into a manageable space rather than a chaotic minefield. Crews operating the Crab needed constant focus, discipline, and coordination, embodying a unique blend of technical skill and battlefield intuition. Their hands-on modifications, adjusting chain length, flail rate, and shock absorbers, improved efficiency and durability, highlighting the importance of field innovation alongside formal engineering. Even after WWII, the principles behind the Sherman Crab informed armored engineering vehicles in militaries around the world. Modern demining tanks, armored breaching vehicles, and mine-clearing systems all draw on its basic concept: neutralize hazards while protecting personnel, maintain mobility, and integrate with broader tactical operations. The Crab proved that effective engineering could shape the battlefield just as much as firepower. Looking back, it's clear that the Sherman Crab combines simplicity and brilliance in a way few machines ever have. What seemed like an experimental oddity became a core component of Allied tactics, ensuring safe passage through deadly terrain. Its story is a reminder that in warfare, innovation often comes from necessity, and that the right engineering solution can save lives, maintain momentum, and change the outcome of battles. In the end, the Sherman Crab is remembered not as a frontline fighter, but as an essential instrument of war, a machine that protected crews, enabled advances, and demonstrated the extraordinary power of engineering in combat. Its legacy continues in the armored engineering units of today, carrying forward the lessons of courage, ingenuity, and practical problem-solving under fire.